For today, we'll be discussing the overview on the economic operations in the power system, particularly discussing the history of the Philippine power system. So we'll be discussing the outline first for the economic operations and control of power system. The outline for this term will be covering the first few days, the overview on the economic operations in the power system, what was the power system look how does the power system look like in the Philippines back then, how did they actually schedule and dispatch generation prior to the liberalization of electricity in the Philippines. How does the Philippine power system look right now? Now we must remember that the power system problem is a quadratic problem, and there are a lot of available optimization techniques to be discussed. Now, what are the basic concepts on the power system optimization after discussing that history? Is that we'll have to start with how Lagrange is used in solving objective with constraints. And with that Lagrange model, how do we use different iterative mathematical iterative processes such as lambda iteration, gradient search, Newton's method, in order to solve a certain optimization problem in the power system. And after that, we'll be using Excel to formulate our basic iterative techniques. Now, once we have a grasp of how optimization is performed, we'll dive more into the details, such as obviously we can't get away from losses in the power system. So how do we handle power system losses in an optimization in a power system optimization problem? How do we know which is really optimal? Is someone that is that may look cheap, but given the amount of losses that it will have to recover, is it really that the most optimal generator to dispatch or to schedule? So how do you translate those losses in economic operations? Now, power system optimization, as since we've already discussed, and by this time we've already discussed economic the basic optimization process for generation scheduling, and we've added losses in it. Now we'll have to add obviously power flow, and now since we're adding power flow, there's a lot of other methods that can be used in power system optimization. So we're gradually increasing more mathematical equations to make the problem and eventually the solution make it more realistic. So we will use linear programming, and with the linear programming, the first basic model that's being used by most students and eventually researchers is a DC power flow model. But when you go to a commercial system, you'll eventually use other methods to incorporate AC. And there's such a thing called an AC-DC iterative model. And how do we, from this model, which is, well, most commercial systems use, how does loss and congestion take part with the optimization? How are they incorporated? So we'll be using what we call sensitivities. Now, once we're done with linear programming, we'll eventually discuss quadratic programming. And with quadratic programming, you're trying to remove that issue with inaccuracies of a linear model. Initially, we discussed a linear model in solving a power system optimization problem. Problem there is, as we've said at the beginning, the power system is a quadratic problem. So whenever you translate the quadratic equation to a linear equation, you obviously lose some accuracy. That's the problem with linear program, but it's easier to solve because it's faster. It's easier to formulate more equations with a linear model. But as far as accuracy is concerned, you're sacrificing some accuracy. That's why some systems are eventually migrating to quadratic programs. After that, how do we will try to incorporate what we call mixed integer programs, and then lastly we'll use Excel solver for simple optimization problems. Now, since we're done, and at this stage, we're done with the power system optimization problem, and we were only discussing generation scheduling as far as energy capacities are concerned. But we'll have to take into consideration that when you're trying to schedule capacities in the system, you have to take into account what we call frequency control ancillary services. By that term, it means these are support systems that help control frequencies, right? Frequency is a great or a best measure to it's the best measure of how the system is balanced between generation and load. So we'll be discussing what are the different ancillary services, particularly in the Philippines. What are the types of frequency control ancillary services? Now, how does that affect the energy or the generator schedules that we have? Now, we'll have to discuss with frequency control and ancillary services, you're scheduling also energy. Thus, we need to have this concept of optimization. How does it work? And eventually, illustratively, we'll show you how optimization works using a basic tool such as Excel solver to highlight or to showcase how to formulate a problem with co-optimization and eventually a solution for that. Um, Now, in some markets, so we've done optimization of energy. We'll be doing co-optimization with frequency control ancillary services. Next up would be how does other markets work in terms of scheduling generators on a day-ahead basis. Now, that's most of the markets use a principle called unit commitment. Now, what's the principle of unit commitment? What is its difference between self-commitment? U.S. markets mostly use unit commitment. Most Asia Pacific markets, such as here in the Philippines, use self-commitment. What is the difference between the two? Will be discussed. Now, for the last part of this course, we'll be tackling power system control, which involves mainly two aspects: voltage stability, and the other one, the commonly managed type of control in power system operations, is frequency control. Under frequency control are the different types or different modes of operation, specifically automatic generation control, and then the free governor mode or the local governor control action.